All right, welcome to the third and final part for today's lecture, and this is going to be a summary of everything we've talked about for the past 4 lectures. The past 4 lectures have been pretty dense. We've gone through things maybe a little bit faster than you would like, but in reality, it's covering a lot of the same topics we've covered before, but with different variables. So I want to go through and make sure that we kind of just summarize everything we've looked at these past 4 lectures. So the first thing we did is kind of look at how everything we've looked at up until this point. We haven't covered all 11 chapters because, we have time for it, but there's no point in making you take Physics 130 twice. It has an angular counterpart. The first thing we did was look at how to describe motion. So we had translational motion, position, velocity, acceleration. How do we take these and convert them to their rotational counterparts, theta, omega, alpha? And so for that, we have conversions. Our translational variable is equal to the rotational variable times r. So in particular for acceleration, we need the tangent acceleration to be related to the angular acceleration. And that's because that's going to cause us to speed up or to slow down. The radial acceleration points in towards the center of the circle, and it causes our object to rotate. So, majority of what we've been dealing with in reality is the tangent acceleration in this class. We've been focusing a lot more on this particular equation. The other one is more important for uniform circular motion, which we did not cover in this class. Once we have our position, velocity, and acceleration for rotational motion, we introduce the kinematic equations, which say that, well, if we have constant angular acceleration, that's the same condition we put on the kinematic equations in the first place. And so with that, we can go through and say, well, we did it for one of these equations. We went through and replaced every translational variable with its rotational counterpart. And it turns out you get the same exact equations, but with the rotational variables. So we can use these in the exact same way we did before, just making sure we used omega instead of v, theta instead of s, x, y, z, r, whatever we had. Time doesn't care what we're doing, so time can stay the same, and alpha for a. We can use the equations in the exact same manner we learned about in the second week of class? Same exact way. We then moved on and looked at rotational dynamics. I understand these tables are not in order. We didn't cover this chapter in order. So, we looked at rotational dynamics. So we had force, now it's torque. Mass, the moment of inertia, because shape matters. Again, acceleration is now angular acceleration, and we can take Newton's second law and apply it for rotating objects. So instead of F is equal to ma, tau is equal to I alpha. Looking at the net torque, direction matters. Is the force causing it to move clockwise or counterclockwise? Based on the coordinate system you have chosen, right? You get to choose, is clockwise positive or not. Usually clockwise is negative, but you can make that decision like we did with all of Newton's second law. We looked at energy. In particular, we had the center of mass, which is our 1/2 mv squared. where V is technically the center of mass moving. When we had rolling, we also needed to consider the rotational kinetic energy, 1/2 I omega squared. So with that, right, we have, when our object is rolling, we have both of these occurring. And then we can go through and plug the total kinetic energy into the conservation of energy. So now we have 2 terms instead of 1. For momentum, again, we are going to be looking at having axis of symmetry in this class. So we can use angular momentum is equal to moment of inertia times angular velocity. But it's not the only, oops, forgot I didn't put that on pencil. It's not the only one we have, right? We have other equations where we can have L is equal to, R cross P. We can have L is equal to RP sine beta. For tau, right, it's not just RF. We have sine phi when we're using our scalars. If we're not using scalars, we also can use the cross product, where again, R must be first, cross F, which must be second. Same with angular momentum. It must be R cross P. And how we go through and use these things is the same way. The laws haven't changed. Energy is still conserved. Momentum is still conserved. Both of these, as long as we use the correct, right, conditions, they're still conserved. It's just we are now using different variables to represent the same ideas. With angular momentum being the weirdest of them all, because we have to make everything angular momentum in order for it to work out. So this is going to be where we end with rotational motion. We haven't, like I spent a lot of time in some of the sections. You will come back to this chapter in Physics 130. I don't know who you'll take for 130. They put different emphasis on different sections in here. But you will see all of these concepts again. So if you have questions, now is a really, really, really good time to ask. So please, if you have questions, ask. And if you haven't taken the lecture quiz, be sure to do so.